Hi, this is a video on Newton's method for approximating solutions to really unwieldy equations. And I'm following the order of topics in James Stewart's calculus textbook. This is in chapter 4, which is on differentiation, and it's the 8th section. We're almost done with this chapter, finally. Okay, so solving nth order equations. Nth order simply, means some number. 5th, 6th, 7th, 8th, 9th, 10th, n stands for any possible integer, basically. So quadratic equations, that is, equations that are raised to the second power, are pretty easy in the vast scheme of things to solve. So you might remember back in Algebra 1, I suspect, where we learned to factor x squared plus 2x, plus 1, that sort of equation. We learned to factor those sorts of equations way back when we first started algebra. And if you're watching this video, there's a good chance you're longing for those good old days. But quadratics are pretty easy to solve. If you can't factor them, we have the good old quadratic equation, which I didn't put here, but you probably are familiar with it. It's negative b plus or minus the square root of b squared minus 4ac all over 2a. And so you might have remembered in Algebra 2 when you just couldn't factor. You had to turn to the quadratic equation where you substitute in the coefficients a, b, and c into the equation and solve. Now, that's happy. There are some really complicated equations or formulas to solve for third and fourth order equations. So a third order equation would be x cubed, or a fourth order equation would be x to the fourth power. Those are pretty complicated. In fact, I think they involve square roots within square roots. Hold on for the ride of your life. It's a story within a story. Anyway, however, there is no formula. Not only is there no formula for fifth order or higher equations, x to the fifth, x to the 400th, x to the 431st power, there are no formulas that exist. In fact, someone in the 1800s showed that it's not possible to come up with a formula that would satisfy those sorts of equations. And so what are we going to do? Well, leave it to Newton. Way back in the 1600s, this is also sometimes called the Newton-RAPHSON method. It's a method of approximation. Boy, approximation in math. What trying times are these? I thought everything was precise in math. Well, not so. And the real world certainly isn't precise. Well, okay, so this is a pretty nice function here. Y equals f of x. Very nice kind of function. There are some more complicated functions in this section of the chapter, and we'll get to some of the problems and caveats at the end. But, okay, so let's take this. And let's say that there's a point here. This point is x1, that's the x value, the x component, and then f of x1 is the y component. So this point is at x1, f of x1. Yay! Now, here's what Newton noticed, being the genius that he was. The tangent, and that's may not be perfectly drawn, but you get the point. The tangent to that point hits the x axis at x2. Now, r is what we're looking for. R is a solution for x. R is a value of x, right? And so at the x-intercept. So we're trying, so you can see that x2, that is the tangent to that point, at that point, is closer than x1. And so what Newton suggested here is that if we use the point slope form to come up with the equation, so y2, well, y2 is 0, because if this is, so this is the one point and this is the other point. And so y2, which is 0, minus f of x1, which is the y1 up here. So y2 minus y1, 0 minus f of x1, equals the slope, which is the derivative at that point, right, times x2 minus x1. x2 being the x component for this point, and x2 being the one there. Okay, now all I do is a little rearranging, and I can solve for x2, which is, remember, x2 is closer to a solution to this equation than x1 is. And so x2 equals x1 minus the ratio of the the actual formula being graphed and the point there. Okay, so this is the gold right here, because what we can now do is, once we have come up with this x2, we can plug it in as x1 and come up with a closer approximation. x3 equals x2 minus that of x2. And so by continuously plugging in, so we plug in x2 as x1 and we solve, and we get a little bit closer to r. And then we plug in, then x4 equals x3 minus f of x3 over the derivative of f of f at x3. And we continue to go. Then we plug it in. x5 equals x4 minus, and x6 equals. And by a successive approximations, we get closer and closer to r as we keep plugging it. This is called an iterative process. And so we come up with this general formula that x to the n plus 1 equals x to the n minus the derivative of x, or the function x of n at xn divided by the derivative at xn, such that the limit as n approaches infinity of xn equals r, which is a solution to this unwieldy equation. Isn't that brilliant? Newton was so smart. I hate him. He's dead, of course. So I've got that on him. I'm smarter than he is now. I'm much smarter than Newton right now. Okay, so here are the caveats. Pick a good first approximation. So there are some really weird functions to where you have to be careful what you pick as your x1, and you do this by kind of graphing it. You can use the graphing calculator to get a general sense of what the graph looks like. And of course you can use that to try to get a solution too. But sometimes graphing calculators are deceptive. Sometimes you have to really expand the graphing calculator to realize that, oh wait, there's something really crazy going on here. But pick a good first approximation, because sometimes if you don't pick a good first approximation, you can end up way off. Now here's the rule of thumb that mathematicians use. When x sub n and x to the sub n plus 1, when they agree to 8 decimal places, you can go ahead and stop. That's good enough. But by the way, you can use this to find square roots. And then finally, with transcendental functions like sine and cosine and tangent, make sure that your calculator is set in radian mode when you're doing this sort of thing. Well, Newton was a pretty smart guy, and I'm pretty envious of him, but hey, we all have our place in life. So this has been Newton's Method.